There we go. Panic. Freak out. All right. All right. Today's lecture starts talking about chemical reactions. Today in lab or in lecture, we're going to learn how to balance. No computers, thank you. We're going to learn how to balance equations, which is something you may already know. It's a bit of your algebra skills. That's one of the reasons that you're supposed to have had algebra before you come into this class. And then we're going to look at types of reactions, both of which are crucial pieces of information in order to be successful in the rest of the course. Now, our foundation we built with nomenclature. If you missed a lot of the questions and you don't understand nomenclature, that is the very first thing you need to remediate after that last Unit 2 exam. Because if you don't have nomenclature down and in your back pocket, the rest of what's going on in this unit is going to be all for nothing, and you're going to be super duper confused. So if you have a hard time with nomenclature, make sure you go through that and review. All right, chemical reactions. We already talked about physical change and chemical change. We did a complete lab on it. Physical change means that the substance doesn't change its chemical formula, which is crucial in this portion of the course. A chemical change means it does change its chemical formula. Physical change examples are things like phase change. When you boil water, it's going from a liquid to a gas. When you melt an ice cube, it's going from a solid to a liquid. Those are physical changes. The water stays as H2O. Chemical changes might be if you did electrolysis. You run electrical current through some water, you can split it up into the oxygen and hydrogen components that's made up of. So how do we know a chemical reaction has occurred? Well, very first information, or very first piece of information you might look at is you see bubbles, right? Alka-Seltzer is a great example. Alka-Seltzer actually generates oxygen gas. So if you ever need a source of oxygen gas for a chemical reaction or an experiment of some kind, you can go down to the grocery store and buy Alka-Seltzer. The other one, what's the one? Alka-Seltzer is CO2, that's right. Alka-Seltzer is carbon dioxide, excuse me. And Effrident, the denture cleaning stuff, is the stuff that generates oxygen. So both of those are chemical reactions. Now, you can take one of those tablets and put it in water and it will start bubbling, but how could you get it to bubble faster? How about if you ground it up? Wouldn't that make it bubble faster? What else could you do to the water to make it bubble faster? Heat it up. You could stir it, agitate the solution. So you can increase the rate of a chemical reaction. You cannot make it react, but you can increase how fast it does react. Another bit of evidence that we're going to be talking about now is this idea of solubility. You are going to make sometimes a thing called a precipitate. And a precipitate is sort of like precipitation that comes out of the sky, except a precipitate happens when you take two liquid solutions that are transparent or translucent, meaning you can see through them. There's not any cloudy substance in them. And when you put them together, they get cloudy. And in this particular experiment that they're showing on this PowerPoint, this is a very famous double replacement reaction that we're going to be talking about in this class. And it's potassium iodide and lead nitrate. And when you put them both together, clear colorless solutions, they look like water. But once you put one in the other, it makes that really bright canary yellow precipitate. Most precipitates that you see in lab are going to be white or gray, but there's some cool ones like yellow and red and brown and black that are kind of cool. A permanent color change also indicates a chemical reaction has occurred. Now, sometimes a change in color will occur and then it goes back. That indicates generally an equilibrium situation, in meaning that it can go back and forth in a chemical reaction. In this class, we talk about completion reactions, so generally they're not going to go back and forth. If it's exo or endothermic, the lab that we did this week was on heat and energy, and you put chemicals together that got hot, you put chemicals together that got cold. That's the idea of exo and endothermic, and if something gets hotter or colder, then generally you can surmise, especially if they start out as room temperature initially, that a chemical reaction has occurred. So when we're writing equations, we have certain protocol that we have to follow, just like in nomenclature. And the protocol includes the fact that we put the reactants on the left side and the products on the right. Now, in this class, we use this completion progression arrow, which is an arrow that goes from the reactants to the products. If you get into Chem 152, after Chem 151, in Chem 152 we use equilibrium arrows, which means an equation can go in both directions. And you calculate the rate in one direction, you calculate the rate in the other direction, and you can determine the overall emphasis, is it forward or backwards reaction. But in this class, we only talk about forward-going reactions. If you have a catalyst, what's a catalyst? Something that speeds it up is generally what the accepted definition, but there are catalysts that slow things down, and sometimes that's important in chemistry. You don't want things to happen too quickly. Things like the carbon rods in a nuclear reactor, those are things that slow the reaction down. So a catalyst just changes the rate. A catalyst does not take part in the chemical reaction. It's not a reactant or a product. So often if there is a catalyst, they will write the symbol for the catalyst over the arrow. And that's because it's not a reactant, it's not a product, it doesn't take part in the chemical reaction, it just changes the rate at which the reaction occurs. State of matter, solid, liquid, gas, that's pretty straightforward. A is gas, B is a liquid, C is a solid. The one that is not as easy to recognize that we're going to be using a lot of in the next couple of weeks is aqueous solution. Does anybody know what that means, an aqueous solution? Generally in water. Up to this point, you guys have talked about it mostly being an acid, but it generally means you put something ionic, an acid or an ionic substance in water, and it's broken apart into its component ions. And we're going to talk about that in terms of solubility in this unit too. So we have solid, liquid, gas, aqueous solution, and then often you'll also see a little triangle sometimes over the arrow, and that means heat is something that had to be used to get that reaction to either go or be a catalyze the reaction. So there's a bunch more symbols that you might use at any given point. Most of you probably have seen those kinds of things in the relationship of this idea of symbolic representation in chemistry. All right, so if you look at this reaction, now at this point you guys have enough information in your brains and with nomenclature that you can say, all right, HC2H3O2 is it's an acid for sure, and it's acetic acid. So you want to say aqueous acetic acid. So you kind of have to look at the whole thing before you start speaking. You say aqueous acetic acid is added to, that's the plus, solid sodium carbonate. And you see the solid is in there. Sodium carbonate is just baking soda. So if you're in an acid to baking soda, you guys have done that before, you put vinegar on baking soda, what generally is going to happen? Going to be bubbles. What are the bubbles going to be? Gas. What kind of gas is up there that might make the bubbles? Carbon dioxide gas is the thing that makes the bubbles. Water is also a product, and sodium acetate is a product as well. So you say and write those. Part of your homework assignment is going to be taking words and translating those into symbols using your knowledge of nomenclature, then balancing the equation and telling me the type of reaction that it is. So you're going to have to use all these skills in composite in the next homework assignment. Diatomic molecules are something that I neglect often at the first part of the course to mention because of the fact that once I mention diatomic molecules, everybody thinks that that's how they always work, that they only work in pairs. That's not true. In their natural state, meaning at standard temperature and pressure, standard temperature is 25 degrees Celsius, about what this room is right now. Standard pressure is 1 atmosphere pressure. That those 7 elements generally exist in their natural state as what we call diatomic molecules. Di, meaning 2, atomic, 2 atoms. And if you think about 777, that will help you remember what the 7 are. Now, that doesn't mean that that's the only way they can exist. No. But when you see something like fluorine gas, chlorine gas, bromine gas, iodine gas, then you go, oh, that's one of those diatomics. Right? Here's where the 777 thing comes in. You see that it starts at element number 7, which is nitrogen, right? Nitrogen is diatomic in its natural state. In this air that we breathe, it's about 78% nitrogen. What we are breathing right now is about 78% nitrogen because nitrogen exists as a diatomic molecule. So that's one of them. Oxygen, you all know, is O2 as a gas. Fluorine is F2, Cl2, Br2, I2. See how it makes kind of a figure 7? How it looks like a 7, right? It starts at element 7. 1, 2, 3, 4, 5, 6. And the last one is the oddball, which is hydrogen over here. That's the 7th one. So there's 7 of them. They make a figure 7, and they start at element number 7. So whenever you see in words hydrogen gas, chlorine gas, bromine gas, oxygen gas, you say to yourself, aha, that's a diatomic molecule. Now, if you see other gases like argon, are you going to put Ar2? No, that's a monatomic gas. Argon and all the noble gases, they don't need to have a pair to exist because they have their natural octet already, and they don't need to pair up with anybody else. Most of the halogens like to pair up because they have only 7 valence electrons. Balancing chemical equations is very much like algebra. The coefficients count for everything behind it. The subscripts only count for that particular element. We have to look at it in terms of coefficients and subscripts. So if you see the entry, like here on the PowerPoint, 3H2O, that means 3H2O, I have 6 hydrogen atoms in that notation and 3 oxygen atoms. Because if I look at H2O itself, and I say, all right, H2O looks like this, all the molecular geometry, right? Here's the H2s and the O's. If I have 3 of those, right, I have 1, 2, 3, 4, 5, 6 hydrogens and 1, 2, 3 oxygens. So the 3 means the number of molecules, and things like the subscripts here mean the number of atoms in a molecule. All right, so there's a big difference between those, and that's part of where your algebra skills are going to be coming in here. When you're balancing equations, you can change the subscript, you can change the coefficients as much as you want. And in fact, in algebra, when I said algebra, we used to call this the check and guess method, right? You're trying to factor equations, quadratic. You start plugging numbers in, you check and guess and see what the factors are. You guys have those nice calculators that you don't have to check and guess so much anymore. But it's the same kind of thing with balancing equations. It's a check and guess. So I would suggest doing the homework in pencil because then you can erase much easier. All right. When you're balancing these, my suggestion is always save oxygen and hydrogen for last because those are often in more than one compound as reactants and products. And if you save them for last and you got something easy like hydrogen gas, H2, or oxygen gas, O2, it makes balancing the whole equation much easier because you can just throw a coefficient in front of those. All right, and then finally you want to get to the lowest whole number ratio of the components in the compound. So if you balance something and you come up with 2H2 plus 2Br2 yields 4 HBr, you want to reduce it to its lowest whole number ratio, which is a 1-1-2 combination rather than a 2-2-4 combination, which you guys all have done that sort of thing before. All right, so if we look at balancing equations, let's take this one. We'll look at it in the context of chemical reaction. So we've got some, what would we call Al2SO43? What's the name of that? It's a sulfate of some kind. What would we call it? Aluminum 3. Actually, do we need the 3 on that one? Nope, don't need the 3. So it's aluminum sulfate. What is it combining with? What's the name of that next stuff? Barium nitrate. Nitrate, right? Okay. And it's yielding, what's it making? Aluminum nitrate and what else? Very good. All right. I'm going to balance this. Barium sulfate. Barium is plus 2, sulfate is minus 2. Is that right? Right? Is that right? Can I copy that right? In the PowerPoint? Al2SO4. Talking right. All right. When you've got parentheses like these, when you've got diatomic ions, my suggestion to students is treat the diatomic ions as a group. Don't try and isolate the sulfur and the oxygen, treat it as a group. So I look at that with 3 sulfate diatomic ions here because of subscript 3. And I've only got 1 over there. Now I can't just throw parentheses and add 3 there because that's changing the nomenclature. I can't do that. But what I can do is I can simply put a coefficient of 3 in front of the barium sulfate to balance the sulfate stack. So I do a little bookkeeping on my own. So now I say the sulfates are okay. I look at the next one. I say, aluminum, there's 2 here. There's only 1 aluminum here. I can't just throw a subscript on it because that's not how the nomenclature goes. What I can do is I can put 2 in front of the aluminum. So now aluminum is okay. Aluminum is okay. Let's look barium here. I've got only one barium here, and I've got 3 over here. I can throw a 3 in front of that one. And now I've got to look at nitrogen. Now this is where it gets complex. Remember, everything in the parentheses you're going to treat like a single unit. If there's 2 of them there, and there's 3 of those entire units, and each unit has 2 of them, 3 times 2 is 6 nitrates on the reactant side. How many nitrates on the product side over here? Not 3. 3 times 2 is 6 nitrates. So now we are balanced. This equation is in fact balanced. Let's double check and make sure. 2 aluminums, 2 aluminums, 3 sulfates, 3 sulfates. 2 times 3 is 6 nitrates. 3 times 2 is 6 nitrates. 3 bariums, 3 bariums. Now this equation follows the law of conservation of matter, which says matter cannot be created or destroyed. If you have problems balancing your equations, generally it's because you haven't figured out the correct nomenclature for the products. And in this next exam, I'm going to give you reactions. I'm going to tell you what kind of reaction it is, and you're going to have to predict what the products are, the correct nomenclature, and balance the equation. So make sure that you are aware those are all skills that you're going to have by the next exam. All right. So here's the kinds of chemical reactions that we're going to talk about: combination, decomposition, single replacement, double replacement, and combustion. Let's see what this animation shows. Remember what this one is. Uh-oh, I might have messed up my screen. There's a couple funny ones I have in here.
There are 5 major classes of chemical reactions. A synthesis reaction is when 2 or more substances combine to form a single product.
There's a good synthesis reaction. Hydrogen and chlorine gas making... Oh.
In a decomposition reaction, a compound breaks down into 2 or more simpler substances.
Never mind then. I can't even get the mouse to work.
A single displacement reaction is when one element takes the place of another in a compound.
Oh, is it that thing that happened last time where it was like split?
No.
Oh, it says no trackpad.
No, that's okay, good. Well, you guys can keep
In a double displacement reaction, the positive and negative portions of 2 ionic compounds interchange.
Oh, it's over there. Okay, I got it. Where are we now? Okay, run over there. Gotta go this way. Okay, there we go. We did that thing again where it split the screens, and instead of mirroring it, it split them separate screens.
Okay, well, I'm not going to show the video anymore. We're just going to go on with the lesson.
Oh, okay.
Yeah, settings.
So it goes to displays. And scroll down.
There it is. Yep, that's the one they showed me how to fix it.
Extend, and switch to duplicate. And then keep changes.
It always defaults to the wrong way.
Yeah, it's weird.
Yeah. Thank you, Larry. Yeah, appreciate it. All right, so let's go through some of these kinds of reactions. Combination. All right, combination. I'm going to give you some examples of combination reactions. I used to do this as a demo in class, but we had a chair 2 chairs ago that found I was doing chemical demos in class, and he said I couldn't do it anymore because we don't have running water and we have carpet in here, so I can't do chemical demos unless they involve water under 80 degrees or household chemicals only. So unfortunately, that wasn't any of these. A combination reaction, also called synthesis. You take 2 small things, you make them into something bigger. The demo that I used to do that I really liked was where I would take and where's Ladybug? There it is. So I take the PowerPoint and do what with it? Minimize it? It won't show what's on the Ladybug here. I'm trying to get what's
on the paper. Is it frozen or something like that on there, or is it plugged in? Yeah. Connection has been terminated. Ooh. I don't know what that's about.
I don't know, maybe we just click on the ladybug.
That's weird. I don't know.
Okay, the demo that I used to do, I would take some steel, oh, you got it? Perfect. I would take some steel wool. Take some steel wool, if you've been in Boy Scouts or Girl Scouts, you might have done this. You can start a fire with steel wool and a small 9-volt battery.
I learned in Girl Scouts, but sounds still cookies.
I know.
No.
So take steel wool, you kind of open it up and get some air in it. Take the 9-volt battery that has the positive and negative on both sides. And you can do it like an A or other battery, but it's hard because of the terminal with positive and negative on each side. The 9-volt battery, the nice little square one, you know what I'm talking about?
Yeah.
It's got the positive and the negative on one side. You take the steel wool and you touch it to the battery, and it will immediately start to conduct electricity because iron, which steel wool is made out of, conducts electricity very well. And it conducts it so well that it gets really super hot enough that if you blow a little bit on it, it will burst into flames. So what I would generally do is I take the hunk of steel wool, I weigh it on a balance, I determine, I say, okay, well, it weighs 7.956 grams. Then I would light it with a battery, I blow a little bit, I get it to ignite, you can see it burn, it made a lot of smoke, the fire alarms go off. And then I would take it off and I would weigh it again. Now, would you expect that the weight would be higher, lower, or no change after I weighed the steel wool after I had burned it? Most people in our common experience, that you burn something, the ashes of that thing are going to weigh less than the original thing does, right? Okay, our common experience, but in this case, it actually goes up almost a whole gram, about 10%. Generally, is what it goes up. The mass goes up. You go, okay, well, I know a chemical reaction occurred. First of all, it was exothermic, right? As soon as I got it started, there was smoke that was emitted, so there's another indication of a chemical reaction. What must have happened to the iron? We added something to it. We did, it's called oxidation, rapid oxidation. What do we call rapid oxidation? Rust, good old rust, okay? So rapid oxidation, you simply are adding oxygen gas, which is a diatomic element, to the structure of the iron, and you make either Fe2O3 or you make FeO, ugly iron, right? FeO, so solid plus oxygen gas. There's two different kinds of iron oxides you can make. Let's balance each of these equations. Look at the top equation. This stuff is going to be solid, right? At the top equation, how can I balance the ions in the top equation? Put 2 in front of the Fe, right? Now I got to fix the oxygens. I got 2 on this side and 3 on this side. Generally, I'd say to students, what's the lowest whole number ratio between 2 and 3? 6. So how can we make 6 on both sides? Put a 3 there and a 2 there. But now my guess and check method isn't working so good because now my ions are unbalanced. So how should I fix the iron? Put a 4 in front of the iron. So now this one's balanced. The law of conservation method has been obeyed. All right, here the iron is okay, but oxygen not so much. So what should I do to the product side? 2. But then I gotta fix the iron by putting in 2 there. All right, so you can form 2 different kinds of iron oxide. This is iron 3 oxide. That's iron 2 oxide. All right. So that's a combination reaction. Another good type of combination reaction, you take magnesium. Every metal will rust. Every metal will oxidize. It just has to be in the right conditions. In this particular case, magnesium is something that once you light it on fire, it does not go out. And it makes a super duper bright light. That's a piece of magnesium that's burning, and they're holding it down in a beaker. They used to make Volkswagen engines out of magnesium because they were light and very strong. What might be a problem with a magnesium engine? It lights on fire and it never goes out. Never. You cannot put it out. Not goes out. And in fact, when I was in high school, and keep in mind, I graduated high school in 1977, way before any of you were born, we used to have desert parties. And when we found this out, guys would go to the junkyard. They'd get an old Volkswagen engine from the junkyard. They'd haul out the back of their pickup truck out to the dunes, we call it, out on the west side. They'd put this big old, they'd dig a big pit. They put the Volkswagen engine under it, and they would start it with a blowtorch because you had to get a really high temperature to get it started. And it would glow so brightly that everyone from miles away knew exactly where the party was because there was this huge bright light. But the problem was it would never go out. And if the cops came and rousted the party, then the thing was burning for a long period of time. We used to sometimes go back after the engine had burned for quite a long period of time, and the sand had turned to glass underneath the engine because it burned so hot and so long. Don't try that at home. Not a good thing to do, but interesting enough. Magnesium is also what's in the road flares. If you've ever seen road flares, you light a road flare, right? It's got to be a flare in terms of if it's raining or anything. Well, we found this out when I was a grad student at Flagstaff, and we found out that it doesn't go out even if it's underwater. So we went to road flares and lit them up and went out to one of the lakes in Flagstaff and threw it into the lake, and it went way down the bottom of the lake where we could see it burning. We did a scientific experiment. We lit one on the ground and had it at the same time as the one that was in the water, and the one that was in the water only went out like 30 seconds before the one that was on land. So they do burn quite a long time, even underwater. All right, this is another combination reaction where you're taking sulfur and oxygen gas and doing a similar thing. And the opposite of combination is decomposition reaction, where you take something bigger and you break it up into smaller pieces. A good example is this stuff right here. I'll bet you know the common name of this stuff. What's the common name of this? Hydrogen peroxide. What's the IUPAC name for this stuff? Dihydrogen. Dihydrogen dioxide. Very good. All right. You can, my mom used to put this stuff on our knees and our elbows when we got road rash, right? When I was in school, we used to play on skateboards and roller skates, and they were ones with metal wheels, not the nice plastic ones like you guys have. And the metal wheels, you'd hit a rock and literally you would stop dead. You know, and so you'd come home with bloody knees and bloody elbows. My mom said she poured hydrogen peroxide. We'd scream and go, ah, because it looks really bad. It's all foamy and stuff, and it doesn't really hurt. Not like alcohol. You pour alcohol on something like that, then you're going to scream. But hydrogen peroxide, what it does is, she thought it was a antibacterial to get the bacteria out. Actually, it was perfect for what she was using it for. Hydrogen peroxide, when it decomposes, the bubbles bring anything that's in there to the surface. And so if you have road rash, a lot of times in the hospital they'll use it. They'll pour it on the road rash because it will bubble all the asphalt stuff out of there as it's decomposing. So it's bubbles, and any sort of organic matter, like your flesh, or bloody stuff, or I had a roommate in college that used to get cold sores inside her mouth, and she would rinse her mouth with hydrogen peroxide. That helped a lot too. I just tell her to swallow it. What do you suppose was making bubbles that the bubbles are when it decomposes? It's good old O2. O2 as a gas, it's diatomic. So what must be left over in the bottle after some of this oxygen bubbles out? H2O. Do you ever wonder why they sell hydrogen peroxide in a brown bottle? Well, yeah, but that's also alcohol. Why would it be sold in a brown bottle that won't let light in?
So it won't separate it.
Well, this particular reaction is photo decomposed. So light is a catalysis for the decomposition of hydrogen peroxide. Now, what you buy in the grocery store is 3%. It's really wimpy hydrogen peroxide. It's in the brown bottle. What we buy in the lab, we use hydrogen peroxide for a lot of chemical reactions. We buy 30%. So it's 100 times as concentrated as the 3% that you buy in the drugstore. We buy 30%. And not only is the bottle brown, but it's like an accordion on the sides. And what happens is, we get it from the manufacturer, the accordion is real smooshed down, right? And the bottle looks like this, with the accordion smooshed down. And over time, the bottle grows. Our lab tech will come in, she'll loosen up the top, she'll smoosh it down again, put the top back on real good, and over time it grows again, and she has to open the lid, smoosh it back down, and it grows again. What's happening? It's decomposing, making oxygen gas, and eventually, it will all bubble out. So if it wasn't in those brown bottles, what would you be buying a bottle of? Water with a few oxygen bubbles in it, right? So you don't want that. You want the good old H2O. All right, so we're going to balance this equation. How do we balance this thing? matter, which says matter cannot be created or destroyed. All right? Single replacement. Single replacement is where one metal will replace another metal. Now, this one is a little bit more difficult to see. We're actually going to do a lab next week where you see a whole lot of these single replacement reactions. And single replacement in general form you see here in the PowerPoint. A is the metal. So this is representing the metal. So you may want to put those in your notes. The A is the metal. BC is an aqueous solution. B is the new metal that comes out of it, and A is the aqueous solution. Before we can talk about this kind of reaction, what I want to talk about is when ionic substances make aqueous solutions, what is actually going on there. So let me show you that. When you take something like sodium chloride, right? We know that sodium chloride is an ionic substance, and it is held together by ionic bonds, and it makes a large crystal structure of repeating sodium and chlorine ions, right? When you put this in water, so now I put my sodium chloride crystal in water. Remember, water is polar. Got the Mickey Mouse ears here, hydrogen and hydrogen. Which side of water is the positive side of water? This side is the positive side, this is the negative side. When we say water molecules are very polar, that means that there is an imbalance of the electrical charges. There are more negative charges on this side of the water molecule and more positives on this side. And what that does is anytime you put water, they call water the universal solvent. And that's because it will dissociate most ionic substances, which is most of the substances on the planet are ionic. And what happens is the water molecules, as it goes up to the sodium and the chlorine, as it comes up, it will be attracted to the sodium, which is positive, and the chlorine is negative, depending on which side the water molecule comes to it. The water molecule will float over here to the crystal of the sodium chloride, and the positive side of the water molecule will now turn towards the chlorine. See how I'm drawing the positive water molecule side? All turning with the positive side towards the negatively charged chlorine molecule. Now, what holds this sodium and chlorine together is the fact that sodium has given up an electron, chlorine has accepted it. This is positively charged, this is negatively charged. The force of attraction holds it together. So there is attraction between them. However, when you get one water molecule, it starts pulling on that chlorine a little bit, not enough to pull it off. But when you get multiple water molecules all ganging up, and they like to choose the ion on the edge of the crystal. If you've ever looked at salt and it's dissolving, the edges of the crystal, it gets round and it gets smaller from the outside first, right? It doesn't break up from the inside. It gets smaller from the outside first. And what happens is these water molecules will gang up and they break that bond and they break that bond and they pull chlorine away and they do what's called hydration. So the first process, when they break this chlorine off and they break those bonds, that's called dissociation. And there's actually an energy requirement for that. As you might expect, when you pull an ion off of a salt crystal, it requires energy to do that. If you take plain old salt and you put it in a cup of water, and you take the temperature of the water before you put the salt in, and then you put a bunch of salt in and you stir it around, the temperature of the water will go down. Why does the temperature of the water go down when you put the salt in? The salt is the water is providing energy to break those bonds between the sodium and the chlorine. Remember, you got to get quite a few of them to gang up on that ion and pull it off of the edge. Then the second part of the process is called hydration, where the water molecules, in this case the chlorine, is surrounded because it's negatively charged. The water molecules turn the positive part of the molecule towards the chlorine, and it's like the little bumper cars in Golfland. You ever heard of those bumper cars in Golfland? The big water. It's like a big inner tube, and you get in it, and you drive it around, and you're the driver in the middle, and you bump another bumper car, right? What happens? You can't combine, you can't touch that person. The water keeps them from recombining by forming these hydration rings. It's called a hydration ring. What happens? Chlorine looks hydration ring like that, looks like that. Sodium, since it's positively charged, it has a hydration ring from the water molecules. But the hydration ring is different. The positive side of the water molecules are facing away from the sodium now. So now, even though sodium, which is now positively charged, and chlorine are attracted to each other, once they come into contact, they bounce off each other because of the fact that they have this ring of hydration. How can I get the sodium and chlorine to reconnect and take them out of the water using physical change? Boil the water on Arizona, just let out in the sunshine for a while, right? And What happens is, as you start taking away some of the water molecules in the hydration ring, right? Take a few of these away here, then all of a sudden they're able to connect and they reform their crystal structure that they have. All right, we're going to talk about the rest of this sort of thing on Monday, but you got a good way to get started on your homework assignment. You can balance all those equations for sure. That's right, study groups are the best way to do it.